Hello student, myself Sarama Malik Das, Assistant Professor of Gargi Memorial Institute of Technology. Today I discuss about theorems on graph. Okay, so our first theorem is prove that the maximum degree of any vertex in a simple graph with n vertices is n minus 1. Okay, so first we see that let capital G be a simple graph. Okay, and capital A be a vertex of G. So let degree of A is equals to K. That means K number of A's are incident to capital A. Okay, that means K number of edges are incidents to capital A. Since there are no loops or parallel edge, as it is a simple graph, so other ends of these edges are distinct. Okay, so there exist k number of vertices apart from A. Okay, so we have k plus 1 number of vertices in this graph. So n is greater than is equals to k plus 1. That means k is less than is equals to n minus 1, which is degree of A is less than is equals to n minus 1. That means the maximum degree of the vertices of the vertex A is n minus 1. Okay, next theorem 2. The maximum number of edges in a connected graph connected simple graph with n vertices is n into n minus 1 by 2. Okay, So here it is given that given capital G is a simple connected graph. Okay, so maximum number of edge in G is equals to number of edges joining any two of the vertices. Any two vertices of G. Okay, so now if there are no parallel edge or self loop, there exists one edge corresponding to any two vertices. So maximum number of edges of G is equals to number of all possible selection of two vertices out of n, that is equals to nc2, which is equals to n into n minus 1 by 2. Next, theorem 3. Okay, this is the sum of the degrees of all vertices in a graph is twice the number of edges in the graph. Okay, so here also we let G be a graph and E be an edge of G. If E is a self loop, then it contribute to sum of degrees of all vertices. Okay, and if E is not a self loop, then it contributes only 1. Okay, so if it connect with V1 and V2, then it contributes 1 to V1 and 1 to V2. That is, that means it contributes 2 to the sum of degrees of all vertices. Okay, so 2 into number of all edges is equals to sum of degrees of all vertices. Okay, so sum of degrees of all vertices is equals to twice the number of edge. Twice the number of edges. Okay. For example, if this is a graph with 3 vertices A, B and C, then sum of degrees is equals to degree of A plus degree of B plus degree of C. That is equals to degree of A is equals to 2, degree of B is equals to 2 and degree of C is equals to 4. That is equals to 8. Okay, and here the number of edge is 4. That means this is 2 into 4. So 2 into number of edges. Okay, next theorem 4. The number of odd vertices in any graph is even. Okay, so we have to prove it. Now let in a graph G, O is equals to set of all odd degree vertices and E is equals to set of all even degree vertices. Okay, so summation of D of Vi of odd, that is equals to sum of the degrees of all odd vertices. Okay, and summation of E D of Vi, this is equals to sum of the degrees of all even vertices. We know this is an even number. Okay, because as degree of Vj, say it is Vj, degree of Vj is even for every Vj in E. Okay, so all are even degree, that means this sum of degrees is also even, of even degree vertices. Okay, so this sum of odd degree vertices plus sum of even degree vertices, this is equals to sum of the degrees of all vertices, which is equals to 2 into number of edges. Okay, from the previous theorem. That means sum of odd degree vertices plus this is also even number is equals to this is also even number as it is multiplied by 2. Okay, that means sum of odd degree vertices is equals to difference of two even number. Okay, which is also an even number. Okay, so it's proved. Okay, so d of bi is even odd for every vertices of bi. Okay, since only the sum of the even number of some odd numbers is even, so we say here the even number in terms is the summation of LHS is 1, LHS of 1, that is the number of odd vertices is even. Okay, so we prove here, that means as it is the even number, that means since the sum is an even number, so the number of odd vertices is even. Okay, next theorem 5. Prove that a complete graph with n vertices consists of n into n minus 1 by 2 number of edges. Okay, now since the graph is complete, and since there is no self loop or parallel edges, so every vertex of the graph has n minus 1 adjacent vertex. That means degree of each vertex is n minus 1. Okay, so sum of all degrees of the graph, that is equals to n into n minus 1. Okay, and we know sum of the degrees is equals to 2 into number of edges of the graph, that is equals to n into n minus 1. So number of edges of the graph This is equals to n into n minus 1 by 2. Clear? So next is theorem 6. The minimum number of edges in a connected graph with n vertices is n minus 1. Okay. Now we let here m is equals to number of edges of the graph. So we have to show here m is greater than is equals to n minus 1. We prove it by induction of m. Okay. Now if m is equals to 0, okay, then obviously n is equals to 1, otherwise g is connected, g is disconnected. Okay, so here m is greater than is equals to n minus 1, as if 0 greater than is equals to 1 minus 1. Okay, now let for m is equals to 1, then n is equals to 2. Okay, when number of edges is equals to 1, then number of vertex must be 2. So here also m is greater than is equals to n minus 1, because 1 is greater than is equals to 2 minus 1. Okay, so let the result is true for k. For k number of edges. Okay, then we have to show here for m is equals to k plus 1, it is true. Okay, so now let G be a graph with k plus 1 edge, and let E be an edge of G. Then the subgraph G minus E. G minus E means we delete, after deleting the edge E, we got G minus E. Okay, so G minus E has k number of edges and n number of vertices. Okay, if G minus E is also connected, then by our hypothesis k is greater than is equals to n minus 1. Okay, so here k plus 1 is greater than is equals to n minus 1 plus 1. That means k plus 1 is greater than is equals to n. which is greater than n minus 1. Okay, and if G minus E is disconnected, then it would have two connected component. Let the component have k1 and k2 number of edges and n1 and n2 number of vertices. Okay, so for the first component, k1 is greater than is equals to n1 minus 1, and for the second component, k2 is greater than is equals to n2 minus 1. So from these two, we have k1 plus k2 is greater than is equals to n1 plus n2 minus 2, and we know k1 plus k2 is equals to k. So it is greater than is equals to n minus 2. Okay, as n1 plus n2 is equals to n. So k plus 1 is greater than is equals to n minus 2 plus 1. That means k plus 1 is greater than is equals to n minus 1. Okay, so the result is true for m is equals to k plus 1. That means by induction method, when the result is true, for k, it is also true for k plus 1, and the result is true for m is equals to 0 and 1 also. So it is true for all m. Okay, so next day we discuss about the others theorem.